Right, I have to do this because we have 2 missing people, so I can't go out to the, I don't want to go to the boards.
They got excused over morning classes. They're probably just sleeping in right now, so I don't think they're.
But it'll be, I think it'll be worse to watch this on video than. All right, so I'm going to give you an in-class assignment in a second to be on task. So be on task. Don't go pull up other material. Don't be looking at your phones. Give me undivided attention and we'll go with no homework deal. But I can come up with homework. I have no problem coming up with homework. So, and then that'll make me pretty grouchy because then I'll be grading over Thanksgiving break. So then I'm grumpy and grading your homework, which is like double whammy. All right, so we have defined the sigma algebra. My feel from just watching you is you kind of have a feel on it. It's a difficult concept. So, you know, not having things 100% and just getting used to that is totally normal for something this hard. So I want to start with something called a measure. And I get asked by my topology class all the time, what's a measure? What's measure theory? Like, actually come to foundations. They're learning it. No, I don't think, I think wherever you go, you just meet that expectation. So I don't think they're worse off. I think the ones who have foundations just have more experience with writing proofs. All right, we start. This is why you needed a sigma algebra. So let F be a sigma algebra. Then mu, yeah, we use Greek letters for this. Sorry, guys. From goes to the positive reals, non-negative reals, is defined to be a measure if, number one, it's got to be positive, but the way I defined it, I already have it non-negative, so it's fine. Getting used to weird stuff. The inputs of this function are entire sets from the sigma algebra. So that set you had for homework, where you had 3 sets, one was the remainder ones, one was the remainder zeros, one was the remainder twos. Those are sets, and you can plug them into this function. So it's not like f of x, you're not in the world of f of x equals x squared anymore. The second property is that measure of the empty set is 0. And the third one, which is always hard to prove, is if AI and AJ are, sorry, not is equal to the empty set. So we call this pairwise disjoint. That's equal to the empty set. No shared elements. This symbol means for all. Go ahead.
Here is that a 0?
Yeah, it's a 0. This should actually look kind of like something you've seen before. If you took 256, you might have seen something like this before. So those are the 3 properties of measure. And the AIs and AJs, they come from the sigma algebra. So think about it this way. Borel sets. Tell me one thing that's in the Borel sets. Do you remember the Borel sets? You got a seed, open intervals are in there, closed intervals in there, singletons are in there. That's what you plug in the measure. You plug in the open interval into the measure and it gives you a non-negative result when you plug it into the measure. The entire open interval goes into the measure. Closed interval goes into the measure. Singleton goes into the measure. So those are the inputs. The outputs are going to be non-negative reals. You've had stuff like this before, you just don't think of it that way. You think of one, determinants. What do you, if you think of the determinant as being a function, what do you plug into the determinant function? an entire matrix. And that's pretty weird. That's very different than plugging in numbers into f of x equals x squared. And what's the output's going to be when you plug in a determinant? It's a real number, right? Do you remember that? Inner product. Inputs would be two vectors of the same length. So you start in Rn cross Rn. Outputs would be a non-negative number. So you've done this before, just that they haven't talked about it this way. So I can give you a quick example of a measure. Define mu to be infinity everywhere except the empty set and define it to be 0. That's called the trivial measure. So I'll wait till everybody writes this down. I actually, I took this class and then I took partial differential equations, and my teacher was saying, he was applying a theorem that needed some conditions on his measure. And I said, but you haven't proved that your measure has these properties. What measure doesn't? I said, the one that's infinity everywhere and 0 at the empty set. He's like, who the hell would use that measure for anything? So it's like one of these creations of mathematics where we create a measure just to be a counterexample for things, but nobody actually uses it. All right, any questions so far? So any ideas of who took 256? Where did you guys see something like this before? Independent events.
Days.
Even before that, just a probability, right? These sometimes are called probability measures. Do you remember when you have independent events and the probability of those independent events turns out to be the sum of the probability of the events? That's property 3. So this is linked to probability. I learned it through partial differential equations. Colonel Clark learned it through statistics. And we sometimes sit together and go, wow, it's actually kind of the same thing. It's bizarre, but it's the same thing. And even if you have two independent events, right, the probability of those two independent events, the union of those two independent events is going to be the probability of the sum. So you can tear them apart, but they have to be independent, which is that condition that I need no shared elements in those events. So if you have a restriction that the measure stays between 0 and 1, it's called a probability measure. So Colonel Clark had to take this class. Colonel Kaminsky had to take this class. So anybody in statistics had to take this class as a class. Are you telling them what you're learning in here? I'm going to ask them. I use this one a lot. Okay. I think I assigned you a homework problem along these lines, but you didn't have the homework problem because I scratched it off. So I want to show you how we kind of deal with this. So if you have in your notes those 3 properties that I gave you. If you look at those 3 properties, which one do you think is the most useful for proofs? To actually do something with, to get your hands on and actually work with. Which one? Second one is measure of the empty set is 0. Does that kind of give you something to work with? Sigma, I know there's so many things to keep straight. Probably the third one. So I'm looking at this, I want to prove it, and I'm thinking, what's my strategy going to be? Well, I want to use the third one. What's the problem with that third one, though? What's the condition to use that third one? They have to be disjoint. So I have to somehow take this A and B and make them disjoint so I can use that third property. So this is my scratch work. And all the stuff that you do for scratch work that I told you before, like write down your no, that still holds. I'm just skipping some of that so I can get through these definitions. But if you're really scratching out this proof on your own, you would actually have to go, this is what I have to show. This is what I know. I have to expand these things. And then I have to have a strategy. So I'm just jumping down to the strategy and saying, doom, doom, doom. I only have property 3 that I could possibly use. It only uses disjoint sets. It requires that. So somehow I have to take this A and B and make them disjoint. So I'm going to take a picture here. I've got my B. This is my set B, and this is my set A. And I want to somehow rewrite them as disjoint sets. So if I took set B and then rewrote it as B intersect A, or let me rewrite that. This my scratch doesn't look very good. So I want B without A in it. So that's this portion right here. But then to total up to B, I have to union A. I'm just rewriting it as 2 disjoint sets. B without A in it, I'm going to throw it out. So that's that green part, and then union up A after it. So now I have 2 disjoint sets. Agree? But so this set right here, so this one right here, let me call it set C. This is C, and this is A. C and A have nothing to do with each other because B is that piece with A thrown out of it. So these 2 sets, C and A, are disjoint. Agree? Do one more move. I'm not sure if I needed it. I don't think I need it, so I'm going to leave it. Here's my proof. I only need this much space. I told you that we need just white paper and a nice pencil as a mathematician. So here's my proof. I don't need much space for this one. The measure of B is the same thing as the measure of B without A in it, union A. Same thing. Those 2 sets total up, but that's the same thing as the measure of B minus A plus measure of A by property 3. Do this. And that's bigger than or equal to 0 plus measure of A by property 1. Boom, done. Measure of B is bigger than measure of A. Property 3. I got 2 disjoint sets. So it's property 3 that allows me to split them. It's yes, because I got right here. The measures of anything are bigger than 0. So I can replace this with an inequality and put 0 here. 0 is smaller than this. Agree? Then I got measure of A, it's less than or equal to measure of B.
How could it be?
It's bigger than or equal.
Alright.
It's property 1. The measure of any set has to be bigger or equal to 0.
But it could never equal to 0.
Or A equals B. You're gonna find some really huge sets have measure 0. The Cantor set has measure 0. The integers have measure 0. I'm gonna show you all that with the specific measure. Good?
So what are, you get like a measure, is it like an integer or is it a set? So you input a set, you get out another set?
Another real number, or non-negative real number, yeah.
Okay, non-negative real, and that's what a measure is, a non-negative real, then
Yes.
it's map back to a set.
It's not 1-to-1.
Okay,
So you would have like things
Oh,
that could go in it that could, yeah.
Okay.
There's more things that give you measure 0 than just the empty set, usually. Depends on the measure I define. But the measures we care about, I'm gonna show you how to integrate with this, like a different way to integrate. So it's really funny because Europeans learn this like freshman year of college. And my TA that I worked with side by side, we came in together. She was from Germany, and she'd always say, you know, yes, we learned this as like our first year in the university. And she goes, but don't worry, I've never done an integration by parts before. I think I got the short end of the stick. I think it's easier to learn integration by parts than to learn this stuff. But she tried to make me feel better. It did not. I don't think I smiled for a year, which is bad for me. All right, we're gonna go right to Lebesgue measure. We're heading right to where we're supposed to go. Raise your hand if you feel you're with me. All right, raise your hand if you feel you're somewhat with me, somewhere. All right. Both, okay.
Yeah, but just the idea of a measure is kind of still abstract.
Yeah, it's, you have to get used to it, so,
Yeah.
which we're not gonna have homework on it, but I don't think like, this class is nice because you don't have to know integration by parts to go to the next class. There's like that prereq. You just have to know how to write proofs and think a certain way. And the more you think a certain way, like this way, you asked me about foundations and the students in topology. It's not that they didn't have foundations. They had so many proofwriting classes that it just doesn't matter anymore. They can write proofs, they can think that way. I can ask them for bizarre examples. They're used to thinking that way. So that's what you get. You get used to thinking that way. One type of proof, like if you learn a proof by, well, you guys did in discrete math. You learned proof by induction. Did it help you anywhere? Really? Did it help you like learn how to write proofs in general? Not really. It's like a technique. So showing you the techniques of writing a proof doesn't really help you write your own proof. Just learning to think that way does. It's pronounced Lebesgue. It's written Lebesgue, Lebesgue. So I need to define for you a couple things before we get to the definition of Lebesgue. I had to find a definition that I could actually give you that you can bite your teeth into. I don't need A to be bounded, but I'm just going to put it there.
What is that first word you mean?
Infimum, I'm defining it. Inf, we just say inf for short. Infimum. So if I have a bounded set of real numbers, it means that I can find, if you plotted those things on the real line, I have a place where number line, I told you is my favorite thing in the world. Number line, there's going to be a place where the dots don't go below the number line, and there's a place on the top where the dots don't go above. They don't have to actually be inside the set. That's the difference here for infimum. The infimum, it doesn't have to be a minimum. Think of arctangent. Arctangent, that y values for arctangent, they are solidly between -1 and 1. But -1 and 1 is never touched. So it doesn't have to be in the set. So definition's not done yet. This is going to take me 2 slides. Let me know when you're ready. Ready? What better way to spend your Monday morning, right? Learning this stuff. There's actually no book out there that has it decomposed like this. It just starts off with, here's a kick in the rear. There's every book I open has just, it starts off with difficulty right away. We do actually. So a greatest lower bound. Let me see. Let me just call it inf. Number one, it's got to be a lower bound, so it's got to squish the set below. And property two, if B is a lower bound, then this has got to be better than it. The best lower bound. I'm not going to define the supremum. It's soup for short. We used to make cracks about the soup being the maximal best upper bound. He is. But I'm not going to write out the same definition. It just, the inequalities all go the other way. Something's the least upper bound if it's number one an upper bound, and number two, if there's any other upper bound, this one's going to do a better job than it. It's going to hug that data set as close as possible.
Explain the infimum.
Infimum is, I'm going to draw a picture so that'll, like, if you have the real number line like this, and you have your points in A or somewhere on here, then this would be the inf of A. And this would be the soup. I made a maxima and minima, but they don't have to be. I'm going to show you a few examples where they don't have to be. So that point here, like if I put a line right here like this, like that, it's a lower bound of everything in the set. Everything in the set is above it. And if there's another lower bound, it's got to be below this one. And we use inf because that allows us not to deal with maxima and minima, which has to be in the set. It has to be attained. The max and min have to be attained by definition. I don't expect you to remember that from Stewart, but in Stewart, they talk about the maximum attaining the max and attaining the min. It's actually touched. So the inf doesn't mean that you actually have to touch it. So I'm going to show you a couple examples. Ready? I'm going to have you to boards in a sec. I just had to load you up with definitions to work with. So if you take this set of real numbers, what's the inf?
0.
0. So it's a lower bound. If you drew 1 over n as a graph, here's n. starts here and it goes down like that, right? Forever, heads down that way. So if I have 0, it's going to be a lower bound. But the points in that set never have to touch 0. If there's any other, if you think there's any other line that I could draw that would be a lower bound, I slide up that lower bound, there's going to be pieces of 1/n hanging below it. So this is the best I can do. So I think of it kind of as a bar that I raise, and I say, how far can I raise that bar until everything it's a lower bound and it's the best lower bound. Because if I eke it up a little bit more, it's going to actually have stuff pooching out underneath it. That's the way it's defined. All right, definition of Lebesgue measure. This took me a whole page, so. And then we'll go to boards. Ready? This is why nobody likes real analysis, but in real analysis, we show that if you have an infimum, there's a subsequence in your original set that has to converge to that infimum. So yes, it's related to limits.
But it's not the same.
It's not the same. I could make a sequence that doesn't have a limit. So I hate people who make these kind of examples, but I'm going to do it. So I could say here it's 0, here it's this, here it's 0, here it's this. I can make a sequence that goes like this. So the infimum is 0, and then it doesn't have a limit. Right, but there's a subsequence that it has a limit. You always have a subsequence that has a limit. There's actually a book called Examples and Counterexamples in Real Analysis, like with stuff like this in it. Like the worst when you get your homework done and then your peer tells you, I think I have a counterexample for what you just. All right. This is going to take me several slides. And then I'll show you a couple examples. Hey, you're the first foundations class that's ever learning this stuff. Like, that's pretty cool. Now I have to know, like, at the end of the semester, I'll ask you, should I do this again? Well, you're leaving, so it's the people behind you. So if you want to hurt them, say, yes, you should do this again. You came on the right day.
Yeah, it's been years since I've been in math like this, so this is fun.
Yeah, you know what? It's you know, the most of our faculty come back here with OR degrees, or they're trying to find a master's degree that doesn't have this class. You guys won't be afraid to do it. You can go take whatever you want. It opens up the ability to take whatever you want. So Colonel Clark is one of those few people that actually did take a legit PhD where they have these kind of courses. So he could come in and teach foundations. He can come in and teach ODEs. He can come in and teach anything in our curriculum as it should be. So you guys can come back here in uniform and teach this class. And then you can teach measure theory in here. Just to sock it to the next group. Yeah. I mean, you also have like, you also have a time limit for, so it's really hard on Army personnel to go to get their master's degrees if they know that they have to be done in 2 years. And then, so do you want to throw this into the mix? But people you admire have done it. So Colonel Clark has done it. Colonel Comiskey also took a very rigorous program. So you can kind of look at them and say, which path do I want to take? The one that opens up my possibilities, I can do anything and go to any program, or limit myself. I don't think at their younger age, I would have thought like that. I would have looked for the easy way out. Just telling you that I probably wasn't the best person to advise, do as I say, not as I did. No, A is less than B in all these cases. Otherwise, it doesn't make sense. The Lebesgue measure for all purposes that you really have to think about is that the Lebesgue measure of an integral or of an interval is just going to be B minus A. It's the length of that A. Suppose I have a subset now of in R that's not an interval. Then we have something called the Lebesgue outer measure. That's where we need the inf, because there's no reason for this thing to be in the set. Of all possible lengths. I'm gonna have to go to the next page to finish this set. But basically what you're gonna do is you're gonna take any arbitrary set that's in the reals, the drawn picture. I have a bizarre set in the reals, it's all over the place. And then I'm just gonna cover that up with open interval. And then take the infimum of these lengths. That's what's gonna happen. So if it's not an open interval, I can cover it up with open intervals. That's topology, actually. I have to finish this set, so let me know when you're done scribbling down this slide. Right. I watch Isaac. He's my meter.
What, man, what's this? The one that
I haven't finished. Or this one. This is the colon, such that it's a length, it's a summation of these length of intervals such that, and I haven't finished the definition. These are parentheses. This is a sequence. It's a set of intervals, just like I've drawn up here. So it covers up that set, just like I've drawn on the board. So all I'm doing is I'm taking a sequence or a bunch of points in R, that's the set E, and then I'm covering them up with open intervals and then squeezing those open intervals down so that they just barely cover up that set. That's the infimum part. If you go back and look at the whole definition, which I don't have on one slide, that's what it is. I'm taking the infimum of all the sums of lengths that cover up that set. So I cover that set up with a bunch of open intervals, and then I calculate the lengths and I squeeze down until I got the smallest possible thing that covers it up and still gives me those lengths. Almost done. For the most part, you just need to work with that outer measure. You don't have to deal with the rest of this. Suppose I take every single set in the real line and it has this property for the outer measure.
What's the symbol above the U?
It's a star. So I should have had it on the other one too. Do I not have it? Yeah, it's there. It's just to distinguish it from the actual Lebesgue measure. That's called a Lebesgue set. And it forms a sigma algebra. We will not definitely be proving that in here. That's called the Lebesgue measure. And that, my friends, is a definition of Lebesgue measure, the easiest one I could find. And I give you a couple examples so you get some intuition for this, because when we think of the measure, we don't actually think of this huge definition. We kind of use just the lengths and just use that. That's pretty much what we do. I've never used this definition except for when they told me what it was. They gave us a few things to prove with it. I had to memorize it for a test. I've never used it more than that. Have you used it? That's the definition. I remember seeing this and just thinking A intersect E. I remember him drawing pictures on the board if I have an arbitrary A and the E complement.
I sit and wonder how Lebesgue comes up with this and says, this is what I'm gonna figure out today.
I think it was all to get around the limitations of the Riemann integral. That was all, like, I got the first paper. It's called the Lebesgue-Stieltjes integral, and it was all to just define integration and then deal with this, the next thing that I'm gonna show you.
I don't like this, so I'm gonna figure out a different way to go around.
I mean, there's no way, like, I think they have something called the gauge integral, which has the same thing, like they're trying to get around the limitations. All right, let me show you two examples. First, if I have E is equal to this, and you can use the fact that the Lebesgue measure is actually a measure, so it satisfies all these properties that I have. Why is this true, the first property? Why can I do that? Property 3, it's always property 3, right? Those two sets that I wrote up here are disjoint. So I can split them off. And then I can use the fact that when it's just an interval, it's going to be a length. So what am I going to get for this? What's the length of the interval from 0 to 1/2? It's greater than 0, it's true, but I want it. It's a half, right? So this part's a half. And this part, 1/2 to 1, another half. So this measure is equal to 1. Huh?
The vague measures.
For this particular example, right? Or what about a single point? What if I added, well, let me go to 1 point. I won't ask you hard questions yet. I'm thinking of hard questions though. I think a lot of the hard questions I ask you on my long drive up. I think I'll ask foundations this question today. All right, let me ask a different question. This is actually one of the cool things. 1.5 hours. Yes, and back. So that's 3 hours a day.
Lots of time to think of the questions.
Yes. Morristown area. Morris County. What's a measure of a point? So let's suppose I have just like 1 point there.
No, I hate to keep interrupting. Is that why you wake up so early to keep the traffic?
Yeah. Well, no, because I'm scared I'm gonna miss our first class, so I get up here early and I work out here and then
But you probably miss a lot of traffic.
there's not very much traffic, like it spins off and goes to New York City,
Ah.
so I don't really get a lot. Measure of a point. What does that equal? You think it should be 0, right? Let's prove it. Feels like it should be 0. Well, X is contained in these intervals. Well, let's see. I can put little open intervals around it. So all I did is I took the X. I hope you're paying attention because I'm going to drop some things for you now next. And if you're not paying attention, those things are going to be really hard. Agree with this? Like I can just take an open interval, this, here's my X, and I can put a little open interval on top of it. From here to, this is -1/k. And X plus 1/k. I can just surround it by a little open interval. And I know that this outer measure of the each one of these IKs are going to be what? It's just the length of this interval. So if I just subtract what's the length of this thing going to be? 2/k. And Josh asked about the limit. So if I could just take this open interval and start squeezing it down to X, right? Because they still cover up X, but they're always going to have length 2/k. So it's really going to be the limit. And what is the length of those lengths head to as I squeeze them down? Yes, if k approaches infinity, what's going to happen to these lengths? 0. Let me see. Those are the infimums, right? The infimums have to be bigger than 0, but they're also heading to 0. So I've got it squished. So the measure of a point is 0 by property. All right, so what's the measure of a countable set of points that are disjoint?
It also be 0.
It's going to be 0 again.
So even if the set is not, for there to be a measure, the set cannot be counted.
Yes.
Okay.
Right, so countable set here. So if I have the measure of these guys, that's the same thing as the measure of x1 union x2 union ... And the only property that's really useful Great. What's the measure of that? 0. So that means the measure of the rationals, going back to Dr. Calkin, is 0. That's a pretty big stat, and the measure is going to be 0. So stay at your desk for this, don't go take boards. Did we talk about the canter set in here? Did it? Taking out the middle thirds of an interval? You didn't talk about that? Alright, maybe, Dr. Doss would love sharing that with you. You can actually move down to number 2, and I'll have him start you out with number 1. And I'll also, you can skip the canter set. I'll have him develop the canter set as a really, really cool set. It's where you take the unit interval and start taking out middle thirds of the unit, each of the chunks. So it's a fractal, but it's countable when you keep doing this. The end result is countable. So you already know what the answer to is. A fractal is something that's self-similar at each iteration. It looks like the previous one, but it's broken up into more chunks.
It was not.
So, can I have you give these to Lucas and Isabel and they come in Wednesday? Keep track.
Give them Wednesday.
Yeah.
Yeah, I'm pretty sure. Pretty sure the same is 0.